All right, so this is the end of the population genetics, and we're going to look at the 5 causes of evolution. And what you're going to find is it's really kind of the opposite of the 5 assumptions of the Hardy-Weinberg theory. So what we're going to do is go through these each and take a look at what they mean, and then push on some of the ideas we're going to expand. So the first one, there are mutations, and mutations occur. The last one said no net mutations. This is, again, the assumption that a mutation has occurred. And here we can see, again, the horse color. This horse in the back here, this tan tone here, that is pretty much the what we believe is the ancestral color of a horse. And then and this little guy up here up front, and then the rest of these are due to mutations. So that could cause a shift in what we call evolution on how horses look. Okay, the next is gene flow, and that is them being transported from one place to another. So here we have all of these green beetles. Well, now all of a sudden a brown beetle ends up over there and starts to breed. So we're introducing new genes and maybe even a new phenotype to that population. And a real life example of this is these vipers, these different snakes, and we have them around Lake Erie. And what's going to happen on these islands, what you'll find is actually for a snake, the best color to be is plain, is not to have the banding. It helps in camouflage on the islands. Now what you got, the islands are small and probably don't have a lot of vegetation on them. And so it actually is best. They've done studies that unbanded is better. But reality is what's happening, because those islands are not that far away, snakes can actually swim, or they're being transported across somehow. And so we have this gene flow. So this banded one pattern, this pattern C, it keeps shifting into the island. So it doesn't disappear because of this addition of new characteristics all the time. All right, non-random mating. This is sexual selection. So this is one very good looking lion. We talk about the Lion King, and who was the big male, and I know Mufasa, that he died, so it's Simba. And it turns out in the lion pride, what the females choose for is that big dark mane. That is sign of health and fitness. Again, I talked about fitness not being about strength or speed or whatever. Depends, everything's different, but in an African lion, it is the males with the large dark manes. That is what's being chosen. And so by natural selection, how you can understand this is then obviously if he has kids, then all the kids are going to have Simba's trait. Now I want to make sure you understand that this is theory, and I want to also make sure you understand that actually who gets to mate is everybody gets to mate in theory. This idea of Darwinian fitness, I want you to understand, is who leaves the most offspring is the most Darwinian fit. But again, everybody gets to breed. It's always been taught that there's this pride of lions and one big male and all these females, this harem, which is true somewhat. But the male will actually tolerate other males, usually lesser males, to help protect the pride. And so what happens is the females are looking to breed, and of course they want their kids to have the best traits, so they will breed with Simba here. But let's say there's a lesser male, let's call him Scar from the movie, and he's walking around and he's trying to breed, and all the females are like, oh, you're ugly, get away from me. But Scar's persistent. So eventually he might get lucky. Female might wear down and allow him. And so what will happen, and the female may choose, hey, I bred with Simba, chances are, but, maybe he's shooting blanks. Maybe I should have a backup. There's different thought processes. So what's going to happen, which I want you to understand, is maybe both of them have kids, but the key here is it's called differential reproduction. Maybe 10 of the kids look like Simba, and then Scar has one. Oh, we feel bad for Scar. Let's give him 2. Okay, so the next generation, there are 10 that look like Simba, and then there's 2 that look like Scar. So differential reproduction or reproducing at different rates will show a trend where they all start looking like Simba. But I want you to understand the importance of differential reproductions. The ones that are reproducing, but not as much, that diversity is important. What happens if things change? What happens if there's a mutation or a problem where all of a sudden Simba's this awesome looking lion, but all of a sudden he has a mutation that all his kids have this really strong body odor. Whereas Scar doesn't have that mutation. And so those kids are better smelling. So in the future, what happens, the females are like, oh man, you're ugly, Scar, but you smell good. So if I just close my eyes and dream of Simba and then have sex with you, the kids would come out looking like Scar. And then you can see over time, you're going to get a leaning now for where the kids will be more like Scar and less like Simba. So that is differential reproduction and actually the idea of natural selection in change. You need that diversity. All right, small population size. Remember the other one was large population size. With a small population, you get something called genetic drift. And genetic drift is just changes due to random chance. So here they're just showing you, we have red, we have white, we have pink. And if you have a low number, only 5 plants survive, maybe they're all just, or maybe 2 survive. It's red by just random chance. And then all of a sudden next, 3 generations away, they're all red. And again, it wasn't anything that happened that red or white or pink were better. It's just that the number of the population was so low, it just happened that all the red ones survived. And so this is the idea of genetic drift. This is why in the assumption a large population needs to be an assumption, because random chance is going to be swamped out if it's a large population. All right, there's a couple of different types of genetic drift I want you to know. One is called the founder effect. And this is where you have a large ancestral population with diversity and then a small population break it off. Here they're showing it on a different island, but it can actually be within a major population. It doesn't really have to leave. It's just they determine for some reason are living together. And on the right is a picture of something that's seen in the Amish. And again, the Amish haven't left the country, but they are a small community back east, and the Amish tend to breed amongst themselves. And so you end up with this very small population, and we do see some genetic disorders like being born with 6 fingers. And again, this is due to the fact that that gene was in that very small population and now can spread. All right, some other examples. So that was the founder's effect. Another one's called the bottleneck effect. And the bottleneck effect, the same thing, is we've got all this diversity on one side, and all of a sudden there's this major die out, killing whatever, and only a few of the individuals get through to the next population. So on in the jar, this is the famous picture with blue, white, and yellow balls inside a bottle, and you pour out 5 of them, and none of the yellow, that's gone. Only 1 of the white survive, and then mostly blue. Okay, bottleneck effect. The Great Prairie Chicken example is the one used in the book, and there was a major die-off of the prairie chicken. This is a grassland species. Some of that has been pulled up because of farming practices, and then there was a drought and some other issues. So they went through a huge bottleneck, and we have really just 2 populations left of the greater prairie chicken, which is becoming a endangered species. So they have certain traits and weaknesses now because of this bottleneck. 2 other species on the right have gone through this. Here locally is the California condor. They have gone through one major bottleneck effect, and that was they got down to just 27 birds remaining in the world. And they had a huge die off. There were hundreds and hundreds of them. And then one season, they just took a dive, and they ended up grabbing the rest of them up. And they were raised in captivity and re-released. And now I believe there's almost over 500 in the wild now. I'm not sure that number, but I haven't checked it. But they are releasing them to this day. So that is an example of a genetic drift that happened locally here. And then on the bottom right is the cheetah. They went through a bottleneck effect in Africa, and they're said they're all kind of related as close as first cousins. And they're worried about diseases, and I think that might be some of the decline. I have an article I'm going to have you read that's a little dated, but it talks about that. So why the cheetahs might be declining still. So we'll have that. And then natural selection itself is a cause for evolution. And so what I want to do with this is really 3 different types of evolution. I want you to know what they look like. And the white here is what the environment is choosing against. So here what they're showing you is diversity in a mouse, all the way from very light to very dark, and then the average population is somewhere in the middle. So 3 different types of selection. One is called directional selection, where the environment is choosing against a color. So in this example on the bottom left directional, they're showing you the light colored ones. For some reason, the light colored ones, maybe it's easy for them to be seen by predators, whatever it is, are hitting the population hard. So obviously over time, you're going to see that population get darker in fur color. That would be directional. So again, the environment is choosing against one of the extremes, this one being the light. It could have been the dark and they've gone lighter too. Either way works, but this is called directional selection. The one in the middle is called disruptive selection. And what happens is the one that is the environment is choosing, you don't want to be average. You want to be light or you want to be dark. And this might be because of habitat again. There might be light places for the lighter ones to hide. There may be darker places for the darker ones to hide. But the medium size, the medium colored one may not have an option. And so they're being chosen against because they are the easiest to see. They can be seen in either environment. And then the last one is stabilizing selection, where that you don't want to be in the extreme. You want to be in the middle. Being too light or too dark makes you vulnerable by the environment. But being right there in the middle is kind of the sweet spot, I guess. And so that is called stabilizing selection. So I want you to know the 3 different types of natural selection, again, directional, disruptive, and stabilizing. And then I will also want you to know what the environment is choosing against in each one of those. And then what's playing sexual selection. So again, I mentioned that Darwin joked about, that damn peacock. He didn't know how to explain how this heavy tail could be an advantage. And what happens with these guys, peacocks can fly. I don't know what you know about peacocks, but they can fly. They're an African species, and they actually live in trees. They'll spend a lot of time on the ground foraging, but at night they will roost in trees to get away from predators. But a male peacock in full display colors for breeding, that tail is heavy, and it takes them a good bit to get off the ground. So you will see these guys, if they're being chased, they'll actually have to run to get enough speed to get their ass off the ground. If not, they become lunch. So Darwin looked at this, saw this, and tried to go, how the heck, having this big, bright, beautiful tail, how does that make any sense with his natural selection? They should be at a disadvantage. They should disappear. What he didn't think about is sexual selection. And what happens is that's what the females like. This is that random mating. This is non-random mating. The females are choosing. And so in this scenario, what are they choosing? They're choosing the best looking male. And for female peacocks, it's really these eyes that make a difference. They've done studies where they've taken this bright, colorful male and cut the eyes off. And then and the females don't like it. And then they're taking a male with a smaller tail and just glued hundreds of eyes on it, and they seem to like that. So it's the eyes, what they call the eyes, that they really are looking for. And what Darwin finally realizes what's happening is the females are choosing these males. And again, it was like, well, man, they're at a disadvantage. But the idea behind this is you're at a disadvantage. You have very heavy tail, you're very brightly colored, you're making a lot of noise. If you can do all those things and still not die, you've got some bitchin' genes. We want to have those genes for our kids. And so that's how he came up with the idea of getting around this. And we see this in a lot of species. Again, in the African lion, it is the big, dark, thick mane on the right. That is a frigate bird. You can see the big red neck. They make boisterous sounds. The pheasants on the bottom left, that brightly colored, very similar to the peacock. And then on the right, in the deer family, and elk and deer and moose, and it would be the antlers. This is something that the males will grow every year. Just imagine the amount of energy it takes to build these things, and then they drop off each year. So again, got to have an advantage to having them. And the last thing we want to talk about is there is no perfect organism. We're not evolving to some magic place. This is the perfect organism. There are problems, and I want you to know the evolution is limited by historical constraints. I can only work with the pieces I have. We don't start from scratch. We always are building off what we have. So that is always going to limit. So what might be perfect in the environment, we may not have something to go there. We have to look around for the species that are there, and what can we use to try to use that niche or that area. Adaptations are often compromises, like wings for birds. They can fly. That's huge, except for they had to give up a pair of limbs. I mean, ideally, it would be better to grow a third set of limbs and have, front and back legs and arms and then wings too. But that is not what happened. So the same with like seals and sea lions, and they have the back flippers that help them swim better. But to do that, they do come on land, and when they crawl around land, sometimes it doesn't look like they can move as easily because they have made the choice. And I'm not sure it's a mental choice, but the choice for the species has been to make them better swimmers. Chance and natural selection interact. So sometimes it's just pure chance. At the moment when things happen, who's there and what gets selected for. Again, maybe two different species, both of them would adapt well to something, but one species gets there at the right time, the other one doesn't. So chance and natural selection do interact. So not everything is choice. We want to make sure you realize it's not always environmental pressure. It just may be chance alone. And the last is selection can only edit existing variations. And so in this idea is the best example of this might be the woodpecker finch out on the islands. It acts kind of like a woodpecker. It's getting insects from inside, but they will use a tool. They'll use a stick to find a hole and bang into that hole to get a bug to come out. A woodpecker probably would be better at it. Definitely would be better at it, but woodpeckers have not made it to the islands. And I mean, I would imagine if you took a woodpecker to the island, it probably would do a lot better, and that woodpecker finch would disappear. If you also did that, I think everybody would kill you because you've just screwed up all kinds of ideas in the Galapagos Islands of evolution. But my guess is that probably would work better. The picture on the bottom is of a snowshoe hare, and they molt and they change colors. And one of the problems with this is they have a timing in their system when they molt and change these colors. With global climate change, what's happening is we're seeing a shift to it snowing later and later. Well, the problem with the molting and the changing of the color is in the genetics, and that timing of that does not change. So now we are getting these very, very white rabbits out in the middle of these still brown forests, and they're very, very obvious. So they are vulnerable before the snow, and we'll be curious to see how that pans out over the years. So we'll stop this and stop the recording, stop the share. And that will be it for population genetics.